Welcome back to the classroom. My name is Mr. Wong. Today we're going to be covering Module 6, Inquiry Question number 3 on Lenz's law and Faraday's law with electromagnetic induction for this particular paper in the 2003 HSC Question 20. So in this question we have two solenoids with hollow cores suspended using strings so that they hang in a position shown here. So we have figure 1 and figure 2. Solenoids are free to move in a pendulum motion. In our first experiment shown in figure 1, a strong bar magnet is moved towards the solenoid until the northern end of the magnet enters the solenoid, and then the motion is stopped. In the second investigation shown in figure 2, a thick copper wire is connected between the terminals A and B at the ends of the solenoid. The motion of the magnet is repeated exactly in this second investigation. Explain the effect of the motion of the magnet on the solenoid in the two investigations. Okay, so let's compare two figures. On this side, on figure 1, I'm going to change color. One of the things we can see is this is a practice of Lenz's law and Faraday's law. Now by moving the magnet here, or moving the magnet, we have a change in magnetic flux, or change in the B field. So obviously that means there's a change in flux, which leads to a production of EMF. So in both scenarios, we're dealing with a conductor, so we should expect EMF to form. Now, the additional part to it is this EMF can induce a current, so it can induce a current so long as there is an electrical path for this current to move. If we compare the pair, this copper wire is that electrical pathway that is required. If we look at figure 1, there is no pathway. So the fact that we do have a pathway would imply that we get an electric field, that changing electric field, or what we can say is the induced current. So induced current can then create a induced magnetic field. According to Lenz's law, this magnetic field must oppose the motion of the thing that originally caused it. That's Lenz's law. So what that means is this B here and this A here, we're going to generate a field if the magnet is trying to move into the solenoid. The solenoid, by Lenz's law, should create a north pole at the front to try and repel, push against it, push it away into this opposite direction, and on this side we should get a south pole because of that. Obviously this aligns with law of conservation of energy because we're balancing the amount of energy of the magnet going in, so the amount of kinetic energy going into here, that's converted into electrical energy to push it back out. Okay, so we're expecting that motion there. So let's try and construct a response that reflects these observations that we have. So let's start off with here. So both induce EMF as the motion of the magnet causes a change in magnetic flux. Okay, the important thing to note is though, only figure 2 will generate a current, as it has copper wires. Okay, so there is that. So what's the consequence of it having copper wires? So we'll just write figure 2 here, just to really show distinction that we are talking about figure 2. And we'll look at figure 1 over here. There's not going to be much said about figure 1, but it's always nice that we do a quick comparison like so. Okay, so figure 2, induced current will generate a B field to oppose the original motion. So in this case, a north pole at B. I do believe it was B. Yep, north pole at B, and the south pole at A. So this causes a repulsion force against the incoming north pole. And we know this is true, or why this occurs, because it obeys Lenz's law and law of conservation of energy there. In figure 1, there is no motion in solenoid because there is no force of interaction. What we could probably also add in terms of the motion of figure 2, the solenoid will move backwards, due to the repulsion with the magnet. You could even try and draw it onto the diagram. So you could say the motion of solenoid will go there, and you can say no motion in the labeling as well. Okay, so that gives an idea of our response. We have shown a cause and effect relationship. We've looked at the motion of the magnets with the solenoid, and we've compared the two different investigations that we have there. So hopefully that's of use to you in explaining how Lenz's law and Faraday's law works, and in the analysis of what happens if we do have a conductive pathway and when we don't. Anyhow, I'm Mr. Wong. Thank you for joining me. Continue on to watch more videos on this current module playlist in the video.